Hello, pre-calc is going to be rationals day 4. So we're going to take a little bit of notes by hand today. And then once we're done taking notes by hand, we'll take a look at one page in your packet. So taking a look at this example right here, f of x equals x squared minus 4 over x minus 2. Today we're going to talk about some exceptions to the rules. So it seems like when we sketch rational functions, we should be able to just go through our critical information, asymptotes, intercepts, make our sketch. But of course, there's going to be a little bit of bumps along the way in the process. And here's an example of what I'm talking about here. So if I was starting to think about, finding asymptotes and intercepts, something that's kind of nice to do is write this in a factored form, right? X plus 2 times x minus 2 over x minus 2. And what I want you to write down for me real quick is the following information. We have a vertical asymptote in this, right? Whatever makes the bottom equal to 0. And we have those two x-intercepts from whatever makes the numerator equal to 0. So we get a vertical asymptote at x equals 2. We get x-intercepts at -2 and +2. So I'll get fancy and write that as plus or minus 2, 0. So what I want you to think about specifically here in question is, we have this vertical asymptote at x equals 2. And if you notice, one of our x-intercepts is also at x equals 2. And that's a big no-no. We can't have that happen. Okay, so there's never a time where a function will ever have a value defined on its vertical asymptote. That's a big problem for us. Okay, so there must be something weird going on here. We can't have an x-intercept in the same location as a vertical asymptote. And it turns out that if I look back to this factored form of the function, that these x minus 2's cancel out from top to bottom. So what we actually can define our function to be is we're going to see f of x equals just x plus 2, that leftover piece, but we're not going to see the whole thing, f of x equals x plus 2. When I cancel those common factors of x minus 2, we're going to see this as long as x is not equal to 2, right? That's where we had that vertical asymptote x-intercept problem there. And what it's going to represent graphically is, hopefully you kind of know what this looks like. Something of the form y equals, I'll give you a hint, mx plus b, right? That's what that format is. But if x can't equal 2, what are we going to see? We're going to see a hole in the graph at x equals 2. And to figure out the specific coordinate of the hole, to get the y value of the hole, all you're going to do is you're going to plug in 2 to the new function. So f of 2 would just be 2 plus 2, which is 4. So specifically here, there is a hole in the graph at the point 2, 4. And now that I have that established, if I go ahead and start making a sketch, I know that this function has a y-intercept of 2, right? According to our b value, if the slope is 1, we're going to rise 1, run 1. And then we're going to rise 1, run 1 again. And that gets me to that point, 2, 4. So at 2, 4, we've got to have an open circle. Any other point we can define on this line, except for the point 2, 4. So if I had you make a sketch of this, it actually is not a rational function at all anymore. It's a linear function. It's a linear function with this value of x equals 2 being excluded there. And that value is called a removable, it's a fancy name. It's a removable discontinuity when you have a hole in the graph. And I think that name makes sense. It's certainly a spot where we're discontinuous, right? If I were to draw my graph, I'd have to jump over the hole and kind of keep going. And why is it removable? Because we literally removed this factor from the numerator and denominator and created that discontinuous place on the graph. We created that hole there. Okay, so let's try another one. If I gave you the example f of x equals, let's do 9 minus x squared in the numerator, and then in the denominator, x minus 3. So now that we know that this is a thing that's out there, right, that we could have holes in the graph, it's the first thing that you want to look for. Can we factor the top and bottom and make sure that, there's anything that cancels? We want to kind of take care of that first. So the numerator would factor through to 3 minus x and 3 plus x. Denominator would just be left as x minus 3. And it turns out that these do cancel, of course, right? X minus 3 and 3 minus x. but they only cancel really if you take out a -1 as a GCF. So you should be left with that -1. So therefore, f of x is equal to, it's up to you if you want to, in this instance, distribute the negative in. So that would be what, -x minus 3. That's the line that I'm left with when I distribute that -1 in. But I'm not going to see that entire line. I'm only going to see that line when x is not equal to, to figure out the x value of the whole, it's whatever makes these factors equal to 0, which would be x equals +3. Right? Similarly, over here, when there was x minus 2's, x equals 2 is where the whole was. Okay, so this is a whole at x equals 3. And if I plug 3 into the function, f of 3 would be -3 minus 3, which is -6. So the very specific coordinate where the whole is would be the point 3, comma, -6. Now that I know that, I know, again, this is a line with a slope of -1 and a y-intercept of -3. So if I go to make my sketch, let's see, 1, 2, 3, 4, 5, 6. So we know, what did I say? The y-intercept is going to be at -3 here. If I go to 3, -6, it's right here. So just make sure that when you draw this line, you draw it with a negative slope. The line's going to look something like this. The other thing I'll tell you is that the calculator doesn't do a great job showing this, and maybe next time we're in class together, we'll graph this together, that if you plug in the original, it doesn't show where that hole is. So I'll show you how we can use the calculator to determine that there really is a hole there, even though your graphing calculator doesn't show it very well. Okay, let's do one more of those, and then we'll kind of skip back on over to the packet for a little bit. So the last thing that we'll do in this section is, let's talk about sketching. This will be number 3, f of x equals, let's do x plus 1 over x squared minus 1. Okay. So when I go to sketch this function, I'm going to, again, think about, are there any holes in the graph? We've got to factor the top and bottom to decide that. And as soon as I factor the denominator or difference of perfect squares, yeah, I see those x plus 1 factors cancel right away. Now, the only thing you really have to be cautious about here is what you're left with is 1 on top and x minus 1 on the bottom. So the last two turned into linear functions with a hole. This is still a rational function. It's a rational function with a hole at x equals, well, let's see how good you are at picking this out here. We're going to see f of x equals 1 over x minus 1, as long as x is not equal to -1. Okay, those common factors that canceled out, the removable discontinuity would be at x equals -1 in this case. Okay, that's where that vertical asymptote and x-intercept would have been. So then really quickly, what's f of -1, just so I can get the y value for the whole? If you plug in -1 for x right here, 1 over -1 minus 1 would be -0.5. Okay, so the hole in the graph is the coordinate -1, -0.5. But making a list of other critical info that's associated with this graph, well, it still has a vertical asymptote. Even though we canceled one of the vertical asymptotes out with the numerator, it still has a vertical asymptote at x equals +1. That's what makes this undefined. It, in fact, has a horizontal asymptote because it's bottom heavy. So we've got y equals 0 for the horizontal asymptote. As far as an x-intercept, doesn't have one of those, right? If you set the top to 0, you get 1 equals 0. But it does have a y-intercept. If you plug in 0 for x, you get a y value of -1 there. So we should be able to generate that info pretty quickly. But the key idea is that now when I make my sketch, I have to make sure, because it's really easy to identify that and then to kind of forget to include it when you make your sketch over here. All right, so let's see. If I look at the critical info we've identified, we've got x equals 1 as a vertical asymptote. We know that y equals 0. The x-axis is a horizontal asymptote. No x-intercept, y-intercept at -1. And we should be careful that at -1, -0.5, which is right about there, that's where you're going to see a hole in the graph. Okay. So it kind of gives you another point to work with in terms of making your sketch. But remember that when you sketch the graph, you should really partition around any special x values, which there's no x-intercept to work with here, but we do have the vertical asymptote at 1. So if you test 0, we already know we're going to get negative because the y-intercept is negative. And oh, by the way, the y value of the whole is negative. If you test something like 2 in the denominator here, 2 minus 1 would be a positive down there. So anything to the right of 1 would be positive. So what that means for your sketch is that to the left of 1, you're below the x-axis. So just don't go through the hole. So you're going to get that curve that looks like this. And to the right of 1, you're above the x-axis, which is going to approach the asymptotes in that fashion. So that's what the graph looks like. The only key major difference now is this exception to the rule where we have the hole at x equals -1. Okay. So if we're good with all of that, let's go ahead and take a look at, in the packet, page 13. On page 13, there's something called a monster rational function. So exciting. All right, so we're going to set the stage here, and then maybe tomorrow we'll make our graph together. So as far as the monster rational is concerned, what we're going to have to do is answer the following questions, because these questions are all a setup towards eventually, maybe tomorrow in class, sketching this together. Okay. All right, what is the common factor in the numerator and the denominator? So that's the first question. So there must be, if I look at these terms across the top and the bottom, something in common. And it turns out right in kind of the middle section there, we have these x plus 6s. So the common factor on the top and bottom is x plus 6. So if x plus 6 is what we cross off, what value of x will there be a point of discontinuity? So based on what we just talked about, right, that hole in the graph, hopefully you're shouting out in the comforts of your own home, x equals -6 is the value where we're going to wind up having a hole. So what we're going to do is we're going to sort of treat this as the remaining parts of the function. We're going to ignore that x plus 6 was ever there, except when I go to make my sketch, I'm going to, at -6, make sure that there's a hole in the graph. And maybe tomorrow in class, we'll work on getting the y value of the hole together. So we'll fill this part in. All right, find the equation of the horizontal asymptote. Well, is it bottom heavy? Is it equal heavy? Kind of indicates, according to the question, that there is one. So because if I multiply out the top, there would be a positive x cubed and the same thing on the bottom. It is equal heavy. And those x cubed terms on the top and bottom would have the same coefficient of 1. So when I divide 1 over 1, you get y equals 1. So that's not so bad. Find the equation of all vertical asymptotes. The vertical asymptotes are what makes the denominator equal to 0. So you've got -2, -3, and 3, right? We're definitely not including 6 anymore, the -6 at that. So we've got x equals -2, x equals -3, and then x equals +3. What are the x-intercepts of the graph? The x-intercepts are what makes the numerator equal to 0. So we've got 5, 2, and then -4. So because it's in factored form, it's pretty easy for us to identify some of this critical info here. So let's write them as coordinates so we don't get them confused with our vertical asymptotes. 5, 0, 2, 0, and -4, 0. And then last thing that we'll do for now is what is the y-intercept of the graph? Y-intercept is a little bit more work. We know we plug in 0 for x. So let's go back up here and say when I plug in 0 for x, the top is -5 times -2 times 4. Right, plugging in 0 for all those x's. The bottom would be 2 times 3 times -3. And let's see, when I do that, I see that these 2's would cancel. So the top is now, looks like -5 times this negative stays maybe with the 4 here. That's +20 over -9. So the y-intercept has a y-coordinate of -29ths. So we'll make sure we include that tomorrow. That's just a little bit bigger than like -2-ish, right? Because -18ths would be -2. So a little, I should say a little smaller than that, right? A little underneath -2. So now that we have this key info, I mean, we went through that pretty quickly. The graph is actually quite complex because we have to do a lot of partitioning. We're going to draw a big number line down here. Look how many partition values we're going to have. All the vertical asymptotes and all the x-intercepts. We're going to have to split this up over. So tomorrow we'll sketch the graph. Once we have the graph sketched, then we should be able to easily determine where the graph is less than 0, where it's greater than 0, and we'll fill in some of the missing pieces from there. So we'll stop here for today. I think it's a good stopping place. If you have any questions, let me know. And then otherwise, we will finish up the monster rational next time I see you in class. Have a great day.